Hello everyone, welcome back to our channel. In this video, we are going to learn about the implementation of all logic gates using only NOR gate. So before going to the implementation, we must know the Boolean laws and the theorems. So basically we have the 5 major Boolean laws that are identity law, null law, deportant law, complement law and double negation, which are all explained in our previous video. If you have not watched our previous video, the link of that video will given in the description. You can watch it and you can continue this video. Along with that Boolean law, we have the De Morgan theorem. Basically, we have the two De Morgan's theorem and we have alternate form for it also. And the importance of this De Morgan theorem is also explained in our previous video. You can watch it and you can continue in this video. So in this video, we are going to implement the logic gates only by using the NOR gate. So the logic gates which we are going to implement are NOT gate, AND gate, OR gate, NAND gate, XOR gate and XNOR gate. So let's move with the NOT gate first. So we already know the Boolean expression for the NOT gate, that is y equals a bar. NOT gate will take the single input and give the single output. Whenever the input is 1, the output is always equal to 0. Whenever the input is 0, the output is always equal to 1. So it acts as an inverter. Whatever the value you give, it will give the opposite to that. It will give the complement of that value. So in the NOT gate, we have only single input, but the NOR gate will take the two inputs. So if both of the inputs of the NOR gate are connected together, then the output becomes not of that input. So that we are going to get the NOT gate. We have the NOT gate expression as y equals a bar. We can able to write this a as a plus a based on the Boolean law. So this is how the logic circuit of the NOT gate will look like when it is designed only by NOR gate. Here, the inputs of the NOR gate are shorted and it is considered as a single input. Whenever the input is A, output will always remain as A complement. Let's move to the next gate. The next gate is AND gate. We know the Boolean expression for the AND gate, that is y equals A dot B. So based on the truth table, the output of the AND gate is always high whenever the inputs of the AND gates are high. So based on the De Morgan alternate form, we can able to directly say that A dot B is always equal to A bar plus B bar whole bar. So this is how the circuit of the AND gate will look like when it is designed by using only NOR gate. So in the first NOR gate, we are giving the input as A so that we are going to get A complement. For the second NOR gate, we are giving the input as B so that we are going to get B complement. The outputs of first and second NOR gate are given as the input to the third NOR gate so that we are going to get A bar plus B bar whole bar. This is equal to A dot B. So let's move to the next gate. The next gate is OR gate. So we know the Boolean expression for the OR gate, that is y equals A plus B. So based on the truth table, we know that the output of the NOR gate is always equal to 0 whenever its both the inputs are 0. OR gate is complement to the NOR gate. When we consider the expression for the NOR gate, we get A plus B whole bar. So if we complement the output of the NOR gate, then we are going to get the OR gate. This is the final circuit that what we are going to get when we design the OR gate using only NOR gate. We have the two inputs that are A and B. The output of the first NOR gate will look like A plus B whole bar. But we need A plus B. So the output of the first NOR gate is considered as the input for the second NOR gate. By that we are going to get A plus B double complement. Here the double complement will get cancelled based on the Boolean law and we are going to get A plus B. Now let's move to the next gate. So we know the Boolean expression for the NAND gate, that is y equals A dot B whole bar. So a NAND gate gives the output 0 only when both the inputs are 1. It performs the NOT operation on the AND output. So right now we already know the expression for the NAND gate, that is y equals A dot B whole bar. Based on the De Morgan rule, we can able to write A dot B whole bar as A bar plus B bar. So that first we need to generate A complement and B complement using two NOR gates with their inputs tied together. Then the output of these two NOR gates are taken as the input for the third NOR gate so that we are going to get A bar plus B bar whole bar. But we need only A bar plus B bar. So the output of the third NOR gate is taken as the input for the fourth NOR gate. So that we are going to finally get the equation which gives the result as the NAND gate. So this is how the circuit of NAND gate will look like when it is designed only by using NOR gate. Here, from the first NOR gate, we are going to get the output as A complement. From the second NOR gate, we are going to get the output as B complement. So the output of this first and second NOR gate are taken as the input for the third NOR gate, so that we are going to get A bar plus B bar whole bar. But we need only A bar plus B bar, so that the output of the third NOR gate is considered as the input for the fourth NOR gate. So the output will become A bar plus B bar whole double bar. The double bar will get cancelled and we are going to finally get A bar plus B bar. So let's move with the next gate. The next gate is XOR gate. Boolean expression for the XOR gate is A bar B plus A B bar. From the truth table, we can able to analyze like the output of the XOR gate is logically high whenever both the inputs are different to each other. This is how the implementation of the XOR gate will look like when it is implemented using only NOR gate. Boolean expression for the XOR gate, that is F equals A bar B plus A B bar. Here we have two operands, that are A bar B and A B bar. Let us consider the first operand, that is A bar B. So we can able to write A bar B as A bar B plus 0. So based on the Boolean law, we know that A dot A bar is always equal to 0. Here we are considering A dot A bar because we need to take A complement as the common. So finally we can able to write A bar B as A bar into A plus B. This is considered as a second equation. Now let us consider the second operand from the equation 1, that is A B bar. We can able to write A B bar as A B bar plus 0. Based on the Boolean rule, we can able to write 0 as B dot B bar. Here we are considering B dot B bar because we need to get B complement as a common. So finally A B bar will become B bar into A plus B. This is considered as the third equation. Now let us put this second and third equation in the main equation, that is equation 1. So we are going to finally get F equals A bar into A plus B plus B bar into A plus B. But in this equation also we have the AND operator. To get the OR operator, again we need to go for the De Morgan rule. So that we are going to get A plus B bar whole bar plus B plus A plus B bar whole bar. This is how the circuit of the XOR gate will look like when we design only by using NOR gate. For the first NOR gate, we are giving the input sets A and B. So we are going to get A plus B whole bar. In the final expression, we are saying like A plus B whole bar whole bar. For the first operator, we need the input as A and A plus B whole bar. Already from the first NOR gate, we have A plus B whole bar. Let us consider the second NOR gate, which has the inputs A and the output of the first NOR gate. So that we are going to get A plus B bar whole bar. So for the third NOR gate, we are considering B and the output of the first NOR gate as the inputs. So that we are going to get B plus A plus B bar whole bar. So the output of these second and third NOR gate are considered as the input for the fourth NOR gate, so that we are going to get the results which are complement to the XOR gate. So we need another NOR gate, so that we are going to get the equation which gives the output as XOR gate. So that the output of the fourth NOR gate are considered as the input for the fifth NOR gate, so that we are going to get the expression which gives the output as XOR gate, which is designed only by using the NOR gate. Let's move to the next logic gate. The next logic gate is XNOR gate. Whenever the inputs of the XNOR gate are same, then only we are going to get the output as 1. The Boolean expression for the XNOR gate is A bar B bar plus AB. So let us consider the first operand, that is A bar B bar. Based on the De Morgan rule, we can write A bar B bar as A plus B whole bar. Let's multiply the second operand with respect to the first operand. so that we are going to get a plus b whole bar into b plus a plus b whole bar. So based on the De Morgan rule, AB equals a bar plus b bar whole bar, we can able to write the equation as F equals a plus b bar whole bar plus b plus a plus b bar whole bar whole bar. So this is the final Boolean expression that what we are going to get when we simplify the XNOR equation with respect to NOR gate. The final logic circuit of the XNOR gate, which is designed using the NOR gate, is shown here. Totally we need 4 NOR gates in order to design the XNOR gate. Let us consider the first NOR gate. For the first NOR gate, we are taking the input as AB, so that we are going to get a plus b whole bar. For the second NOR gate, we are taking the input as a and a plus b whole bar, so that we are going to get a plus b whole bar whole bar. For the third NOR gate, we are considering b and the output of the first NOR gate, so that we are going to get b plus b bar whole bar. So the output of the second and third NOR gate are given as the input for the fourth NOR gate, so that we are going to get the final expression which gives the output as the XNOR gate using the NOR gate. So this is how all the logic circuits are designed only by using the NOR gate. Let's move with the summary. We have the Boolean expression for the each gate and number of NOR gates that required to design that particular gate. So in order to design the NOT gate only by using the NOR gate, we need a single NOR gate. So in order to design the AND gate using the NOR gate, the minimum number of NOR gate required are 3. So while designing the OR gate, we need at least 2 NOR gates. To design the NAND gate, we need at least 4 NOR gates. To design the XOR gate, we need at least 5 NOR gates. And to design the XNOR gate, we need only 4 NOR gates. So this is all for this video. Let's meet in the next video. Till then, bye.